Cell 1. In this exploration, we're delving into the comparative advantages and disadvantages of two prominent data manipulation libraries that developers and data analysts frequently turn to: Pandas and Polars. When we think of Pandas, it stands out for its extensive ecosystem, which includes a wealth of documentation, tutorials, and community support. This makes it exceptionally user-friendly, especially for those who might be newer to data manipulation. Its intuitive interface allows users to perform complex operations with relative ease, akin to navigating a well-organized library where every book is clearly labeled and easy to find. Pandas is particularly effective at handling small to medium datasets, ensuring that processes like data cleaning, transformation, and analysis can be executed without a hitch. However, there are important considerations to keep in mind when scaling up. As datasets grow larger, Pandas can start to exhibit performance limitations that may not align with the needs of more demanding applications. For instance, it can struggle with latency issues when processing massive data frames. Additionally, there's the potential for memory problems arising from hidden copies of data that Pandas might create during operations, much like having multiple versions of the same document cluttering your workspace. In contrast, Polars emerges as a formidable alternative, especially for those seeking speed and efficiency. It's designed to be faster and more memory efficient, leveraging features like multi-threading and lazy execution. This means that, unlike traditional eager evaluation, where operations are computed immediately, Polars can optimize the processing of large datasets by deferring computations until absolutely necessary. This approach allows it to handle significantly larger volumes of data without bogging down system resources, analogous to a skilled chef who can prepare multiple dishes at once without compromising on quality or timing. However, adopting Polars does come with its own set of challenges. For those who are accustomed to Pandas, the transition may require some adjustment. The ecosystem surrounding Polars, though rapidly growing, is still more limited in comparison. There are fewer resources and a smaller community to draw upon. As a result, users may need to invest time learning its idiosyncrasies and adjusting their workflows. This nuanced overview becomes essential for anyone faced with the decision of which library to utilize for their projects. Your specific needs, particularly in relation to data size and the efficiency of processing tasks, will play a crucial role in determining the most suitable option. Understanding both libraries allows you to align your choice with your project goals, ensuring that you leverage the right tools for your data challenges. Transitioning from theoretical considerations to practical implementations can illuminate the path forward in your data manipulation journey. Cell 2. In this cell, we begin our journey by meticulously setting up the environment, a crucial step that lays the foundation for our analysis. We start by importing necessary libraries, such as NumPy, Pandas, and Polars. These libraries are powerful tools that enable us to manipulate and analyze data efficiently. To maintain clarity in our output and avoid distractions, we take the additional step of suppressing warnings that might otherwise clutter our view. Next, we delve into creating a synthetic dataset that mimics real-life transaction activity, generating a staggering 200,000 transactions. This dataset is not arbitrary. It features various columns meant to capture essential aspects of each transaction. We include transaction IDs, customer IDs, and transaction amounts, as well as details about the merchant involved, the channel through which the transaction occurred, and the country where the transaction took place. Furthermore, we incorporate timestamps to provide context regarding when each transaction happened. And to add depth, we include a risk score that quantifies the likelihood of fraud or disputes associated with each transaction. By utilizing random functions, we ensure that the generated data reflects realistic distributions, imitating the diverse, unpredictable nature of financial data in the real world. To add an element of complexity that further aligns with actual financial scenarios, we introduce missing values in the merchant column. This kind of missing data can commonly occur in real-world datasets, often as a result of system errors or inconsistencies during data collection. Additionally, we simulate refunds by including negative transaction amounts. This feature mirrors the reality that not all transactions are straightforward payments. Customers often return items or request refunds, and it's essential for our dataset to account for these situations. Once our dataset is generated, we take a moment to display the first few rows of the data frame. This initial glimpse offers valuable insights into how the generated data looks, enabling us to verify that the structures and values align with our analytical objectives. Visualizing this data helps us ensure our future analyses and models will be built on a solid, representative foundation. This cell skillfully establishes the groundwork for further exploration and analysis, producing a robust dataset that reflects potential real-world transaction patterns. As we move forward, we can build upon this synthetic data to unlock deeper insights and formulate more sophisticated models. Cell 3. In this cell, we are embarking on a straightforward yet essential journey, demonstrating how to transform a Pandas data frame into a Polars data frame. To begin with, the first line of our code serves as an important verification step. Here, we check the type of our original data frame, labeled DFPD. This line is crucial as it confirms that we are indeed working with a Pandas object, which is the foundation for our subsequent operation. Think of it as checking the ingredients before starting a recipe. You need to know what you have on hand before proceeding. Once we've established that DFPD is in fact a Pandas data frame, we move on to the conversion process itself. This is accomplished by invoking the fromPandas function from the Polars library, which serves as our bridge between the two different data structures. By executing this function, we facilitate the creation of a new data frame, which we store in the variable dfpl. Imagine this step as transferring a carefully assembled dish from one plate to another. While the presentation may change, the core flavors and ingredients remain intact. After completing this crucial step, we take a moment to verify our work by printing the type of the newly created DFPL. This line of code is not merely for reassurance, but serves to confirm that our transformation has succeeded and that we are now operating with a Polars data frame, which opens up various avenues for optimization and analytical efficiency. The significance of this conversion cannot be overstated. It allows us to capitalize on the performance advantages offered by Polars, particularly when handling large datasets, while starting with data initially loaded into Pandas. By leveraging Polars' efficient processing capabilities, we can effectively enhance operations that might otherwise be cumbersome in Pandas. This shift is particularly beneficial for scenarios that involve extensive computations, such as aggregations or complex data manipulations, making our data analysis workflow faster and more efficient. As we explore the features of both libraries, we begin to appreciate the unique strengths they offer, paving the way for richer data manipulation experiences. Cell 4. In this particular code cell, we delve into the topic of saving data frames using both the Pandas and Polars libraries, two powerful tools widely used for data manipulation and analysis in Python. Through this process, we specifically work with a data frame named DFPD, utilizing the Pandas library to perform two essential operations: exporting the data to a CSV file and also to an Excel file. It's important to note the deliberate choice to exclude the index in the output files. Excluding the index can often streamline the data, making it more user-friendly for those who might not be as familiar with the structure of data frames. For instance, if someone were to open the CSV or Excel file in a program like Microsoft Excel, they may find it cleaner and more intuitive to read if extraneous indexing details are omitted. On the flip side, we turn our attention to the Polars library, where we focus on the data frame referred to as DFPL. Just like with the Pandas export, the goal here is to save the data into both CSV and Excel formats. The process in Polars is notably straightforward and often leverages the library's performance advantages, making it exceptionally efficient for large datasets. Imagine a scenario where you're handling millions of rows of data. Polars would typically allow you to export this data much faster than traditional methods. This operation, saving data frames to widely recognized formats like CSV and Excel, is not just a technical task. It serves a pivotal role in the realm of data science and analytics. Making data accessible in these familiar formats simplifies sharing and integration with other tools and platforms. For example, a colleague receiving the CSV or Excel files can easily open them in their preferred software, conduct analyses, or even perform simple modifications without needing to run any Python code themselves. Additionally, these formats are often supported by various data visualization tools and client applications, enriching the possibilities for collaboration and data-driven decision-making. Overall, mastering these exporting techniques facilitates a smoother workflow, enabling researchers, analysts, and teams to communicate insights and findings far more effectively. As we explore the process of saving and exporting data, we'll uncover further details that can optimize our approach, allowing us to harness the full power of these libraries. Cell 5. In this cell, we delve into the fascinating world of data manipulation by examining how to efficiently read data from Excel and CSV files, leveraging the robust capabilities of both the Pandas and Polars libraries. To begin our exploration, we start with Pandas, one of the most popular data manipulation libraries in Python, well loved for its ease of use and versatility. The process initiates by importing data into a Pandas data frame using functions like readCSV and readExcel, which serve as gateways for reading structured data. After the data is loaded, we take a moment to display the first few rows. This snapshot not only provides a quick overview of the dataset structure, but also allows us to get a feel for the kind of information we're dealing with, much like flipping through the first few pages of a book to gauge its content and style. Next, we shift our attention to the Polars library, a relatively newer entrant that is quickly gaining traction within the data science community. One of its most noteworthy attributes is its performance advantage, particularly when dealing with large datasets. This performance boost becomes apparent as we use similar functions to read data from CSV and Excel files. While Pandas is capable of managing data effectively, Polars is designed for speed and efficiency, which is akin to comparing a traditional bicycle with a sleek, high-speed racing bike. The ability of Polars to handle larger datasets without a hitch allows data scientists to work with more comprehensive data collections and complex analyses seamlessly. As we delve deeper into Polars, we introduce an intriguing feature known as lazy scanning. This feature optimizes data handling by allowing us to defer the actual loading and computations until absolutely necessary. Imagine reading a book, not page by page, but rather just skimming through to find the chapters that interest you the most. Lazy scanning can help manage large datasets by not loading everything into memory at once, which can be a game changer when working with massive quantities of information. It conserves resources and enhances performance, making Polars an incredibly compelling choice for those who are tasked with juggling big data scenarios. To encapsulate our exploration, we print the type of the lazy frame at the end of our analysis, emphasizing its unique characteristics. This step reinforces our understanding of how the data is being treated in memory and the potential it holds for future calculations or transformations. Overall, the transition from Pandas to Polars not only expands our toolkit for data manipulation, but also highlights the evolving landscape of data processing technologies, each with its own strengths and advantages to match various use cases. Cell 6. In this particular code cell, we delve into the fundamental distinctions between mutable and immutable data types, focusing on two widely used data manipulation libraries, Pandas and Polars. These libraries are staples in the data analyst's toolkit, each offering unique capabilities suited for various tasks. To begin with, let's take a closer look at Pandas. This library embraces a mutable design, which means it permits in-place modifications. As we examine the code, we see a practical example of this feature illustrated through the adjustment of the customer ID and merchant columns within a data frame. Here, the customer ID column is transformed into an integer type, while the merchant column is converted to a string type. This conversion is not just a technicality. It plays a vital role in ensuring that data is organized in a format suitable for subsequent analysis, enabling clearer insights and more straightforward calculations. Picture it like reshaping a jigsaw puzzle. Adjusting the pieces to fit correctly allows for a coherent picture to emerge from what might otherwise seem like chaos. Shifting our focus to polars, we find a stark contrast in its approach. Polars is built with immutability in mind, which means that whenever you aim to modify data types, the library doesn't alter the existing data frame directly. Instead, it generates a new data frame that reflects the desired changes. This is akin to crafting a new sculpture from a block of marble rather than chiseling away at the existing one. Every transformation yields a fresh masterpiece. After these transformations, the code proceeds to print the schema of the newly created data frame, providing a concise summary of the various data types contained within it. This clear presentation allows for easy identification and understanding of the structure of the data, facilitating further inspection and analysis. This comparison not only highlights the operational differences between pandas and polars, but it also underscores the significant role that these architectural choices play in data management. Ultimately, selecting the right library boils down to the specific needs of your project. Whether you require the flexibility of in-place changes or the safety and clarity of working with immutable data structures, understanding these nuances can empower data professionals to make more informed decisions tailored to their unique analytical challenges. As we continue to explore these libraries, we'll uncover more intricacies that can significantly impact how we work with data effectively. Cell 7. In this engaging exploration of data manipulation, we dive into the process of selecting or filtering rows from two distinct data frames, utilizing the powerful libraries known as pandas and polars. Imagine these libraries as highly skilled assistants in a vast library of data, each with their own unique strengths. Here, our aim is quite precise. We are looking to extract specific entries from these data frames, where the amount exceeds 100 and the country is identified as the United States. This kind of targeted filtering allows us to hone in on essential transactions, akin to a detective sifting through a stack of papers to find the most relevant clues. For our first approach, we turn to the Pandas library. This library is renowned for its user-friendly syntax and rich functionality, making it a favorite among data analysts. We start by creating a new filtered data frame based on our criteria. By applying the appropriate filters, we can select rows that meet our conditions. Once this new data frame is formed, we display its first few entries, giving us a clear snapshot of the relevant transactions. This practice not only enables us to quickly assess the data, but also allows for a more profound understanding of the context behind each amount. Imagine flipping through a photo album where each picture represents a unique transaction, instantly providing insights into our financial inquiries. Next, we turn our attention to the Polars library, which is celebrated for its efficiency and speed in handling large data sets. The process here is quite similar. We perform the same operation and utilize its efficient filtering capabilities to achieve the same goal. With Polars, the syntax might be slightly different, but the outcome remains consistent: an organized data frame that clearly outlines our specified criteria. By examining the filtered results from both libraries, we can cross-compare the entries, revealing any discrepancies or unique insights that each tool might offer. The outputs from both data frames serve a significant purpose, as they will enable us to analyze specific records that align with our defined criteria. This step is crucial for targeted data analysis, allowing us to draw informed conclusions based on the transactions highlighted in our filtered results. Whether we're assessing financial performance, conducting market research, or identifying trends, this meticulous filtering process lays the groundwork for deeper insights. As we navigate through these libraries and their functionalities, we find ourselves better equipped to tackle complex data challenges ahead. Cell 8. In this particular scenario, we are delving into the intricacies of creating and updating new columns across two distinct data frames, using the powerful libraries of Pandas and Polars. These libraries serve as essential tools for data manipulation and analysis in Python, each with its own unique strengths and syntax. For the Pandas data frame, our focus is on enhancing our dataset by adding a new column that signifies whether a transaction is a refund. This is determined by checking if the transaction amount is negative. In practical terms, if you imagine a store returning a portion of money to a customer, the amount logged in the transaction record might appear as -50. By designating this amount with a specific column, we make it much easier for anyone reading the data to immediately identify refunds amidst regular transactions, which might be positive values like 75 or 100. Moreover, we introduce an additional column that captures the absolute values of the transaction amounts. This column essentially strips away the sign, ensuring that every value is represented as a positive figure. So whether a transaction shows an income of 200 or a refund of -50, the absolute value column simplifies visualizations and comparisons, allowing analysts to see the true scale of transactions without getting bogged down in the negativity of refunds. Furthermore, we incorporate another column that formats the transaction month as a string, allowing us to capture the month directly from the date of the transaction. For instance, rather than just seeing a date like 2023-10-05, we translate that into something more user-friendly, like October. This string formatting is particularly beneficial for time-based analysis, as it allows for more intuitive grouping and filtering by month names, enhancing clarity in our datasets. Shifting our focus to the Polars data frame, we execute similar tasks using the concise and efficient syntax that Polars offers. In this instance, we achieve the same objectives, creating a column to identify refunds, another for the absolute amounts, and a third for formatted month strings. Although the syntax differs, the end results align closely with what we achieve through Pandas. This emphasizes the versatility and capability of both libraries, giving you options based on the specific needs of your analysis. The implementation of these transformations in both data frames is vital for enhancing the overall clarity of the data. When we present these datasets, we can reveal valuable insights that might not have been immediately apparent. For example, aggregating the total number of refunds by month could highlight seasonal trends in customer returns, or the total transaction amounts could help monitor sales performance. Finally, to encapsulate the impact of these modifications, we display the first few rows of both data frames. This visual representation makes it easier for stakeholders to grasp the changes we've enacted and appreciate how far we've come in processing and interpreting our data. With these tools and transformations at our disposal, we pave the way for deeper analytical endeavors as we continue to explore our dataset. Cell 9. In this section, we delve into the intricate world of transaction data analysis, honing in on the art of performing group-by aggregations. Our primary focus is to dissect this data according to two important dimensions: the month of the transaction and the channel through which it occurred. This layered approach allows us to unravel significant insights hidden within the data. By dissecting our transaction analysis, honing in on the art of performing group-by aggregations, our primary focus is to dissect this data according to two important dimensions: the month of the transaction and the channel through which it occurred. This layered approach allows us to unravel significant insights hidden within the data. By dissecting our transaction records in this manner, we aim to derive several critical metrics that can illuminate the overall performance of our business during specific time frames. First and foremost, we will calculate the total count of transactions, giving us an overview of activity levels. Imagine it like a bustling marketplace. Counting how many customers visited during a week helps us understand peak times and tailor our services accordingly. Next, we will compute both the total transaction amounts and the average value of those transactions, offering us a clearer picture of not just how many purchases were made, but how substantial those transactions were. This is akin to analyzing a restaurant's sales, knowing not just how many meals were served, but also the revenue generated helps in developing marketing strategies. An additional layer of complexity in our analysis involves assessing the high risk rate of transactions based on established fraud indicators. This is crucial in today's digital age where vigilance against fraudulent activities is paramount. By identifying patterns or anomalies that suggest a transaction may be suspicious, we can better protect our business and customers. To facilitate this analysis, we will employ both the Pandas and Polars libraries, each renowned for their powerful data manipulation capabilities, but offering different strengths. By showcasing similar operations in these two environments, we illustrate how adaptable one can be in handling data tasks, much like a chef who can create the same dish using various cooking techniques. The final output from our meticulous process will be a neatly structured summary of the aggregated data for both libraries. This summary will encompass only the first few rows of our findings, acting as a concise snapshot that reveals transaction trends and highlights potential risks. Ultimately, these insights are not merely numbers on a screen. They are the foundation upon which informed business decisions can be made. For instance, understanding seasonal peaks in transactions can lead to strategic marketing bursts, while identifying high-risk periods could ensure enhanced security measures during those times. As we move forward, we will explore the specific methods employed in each library, setting the stage for a deeper dive into these powerful tools for data analysis. Cell 10. In this code cell, we delve into the task of sorting data by leveraging two prominent libraries, Pandas and Polars. This process is particularly vital for effectively organizing our aggregated data, ensuring that we can readily access and interpret the information we need. Sorting allows us to establish order within our datasets, making them easier to analyze and understand. To begin our exploration, we find ourselves focusing on a data frame named AgPD, which serves as a representation of our aggregated data. The cell initiates the sorting process by organizing this data frame first according to the month column in ascending order. This means that the data will be arranged chronologically, allowing for a clear temporal understanding of how values develop over time. Following this primary sorting criterion, the code then sorts the data frame by the AmpSum column in descending order. This dual-level sorting method is akin to stacking books on a shelf. First, you arrange them by genre, the month, and then, within each genre, you order them by their height, the amount. The result is that we get to see not only which months are represented in our data, but also highlights where the significant sums lie within those months. After executing this sorting operation, the cell proceeds to display the top entries of the sorted data frame. This provision gives us a quick but informative snapshot of the results, allowing us to get a sense of the most prominent figures within our dataset at a glance. This approach is akin to flipping through the first pages of a book. It provides a preview of the content that awaits. Shifting our focus, we then perform a similar sorting operation using the Polars library on an alternate data frame named AgPL. Polars, being a newer entrant in the data manipulation space, showcases its own unique methods for achieving the same goal of data sorting. This comparison emphasizes the versatility of both libraries. While their syntaxes and underlying architectures may differ, they ultimately serve the same purpose of helping us organize our data effectively. By examining the outputs generated from both libraries, we obtain a valuable opportunity to compare their performance and functionality side by side. This comparison is crucial in the realm of data analysis, as it not only assists in determining which library might be more efficient or user-friendly for our purposes, but also enriches our overall understanding of data manipulation techniques. Both Pandas and Polars have their strengths, and the choice between them can depend on the specifics of the project at hand, the size of the dataset, and the user's familiarity with either library. As we proceed, we will further explore the implications of these sorting techniques, potentially uncovering deeper insights into the nature of our data and the tools at our disposal. Cell 11. In this section, we are delving into the important issue of missing values found within two distinct data frames, utilizing the powerful capabilities of the Pandas and Polars libraries. Missing values can often lead to skewed analysis or even erroneous conclusions, which is why it's crucial to handle them appropriately. First, let's explore how we tackle this issue with the Pandas library. In particular, we will focus on the merchant column of our data frame. This column, much like a vital artery in a bustling city, carries essential information that connects various parts of our analysis. To address the presence of null entries in this column, we fill these gaps with the string unknown. This simple yet effective strategy allows us to ensure our dataset is more complete and ready for useful analysis. Once we perform this operation, we take a moment to display the updated data frame. This step is akin to reviewing a map after changing a route, just to confirm that everything is in order and accurately reflected. By doing so, we bolster our confidence that the data we are working with can lead to insightful conclusions. Next, we shift our focus to Polars, another powerful library that has garnered attention for its speed and efficiency. Here, we will perform a similar operation to replace those pesky null values in the merchant column, using Polars' unique syntax. This process is not just a mechanical task, it's about fortifying the integrity of our data. Think of Polars as a high-speed train that helps us travel through our dataset quickly, ensuring we don't get bogged down by any missing pieces of information. Just like in Pandas, after executing this operation, we would display the updated data frame. This display serves a similar purpose. It allows us to inspect the changes and reassure ourselves that our data is now more robust and ready for further exploration. By effectively addressing missing values in both data frames through these libraries, we are not merely filling gaps. We are reinforcing the foundation of our future analyses. This careful approach ensures that we're steering clear of potential pitfalls that could arise from having incomplete data. Now that we have tackled the issue of missing values, we can confidently progress to the next stages of our data analysis journey. Cell 12. In this code cell, our primary focus is on the important tasks of renaming and dropping columns within data structures, utilizing two powerful libraries, Pandas and Polars. These libraries are popular in the data science community for their ability to handle large data sets efficiently. The cell begins with a specific operation aimed at increasing clarity in our dataset. We take a column labeled TXNTS, which represents the timestamp for transactions, and rename it to a more descriptive term, timestamp. This change isn't just a minor adjustment, it plays a significant role in making the dataset more intuitive. Think of it as labeling a drawer labeled miscellaneous to office supplies, making it easier to find what you're looking for at a glance. After this initial step, we also make a deliberate decision to remove the amount abs column from the data frame named DFPD. This column might contain data that is extraneous or redundant for our current analysis. By dropping it, we streamline our dataset, allowing us to focus on more relevant variables. Having clutter-free data enhances the effectiveness of our subsequent analyses, as it reduces noise that could lead to misinterpretation of results. To provide a clearer picture of our amended data frame, we take a moment to display the first few rows, giving us a snapshot of what our clean data now looks like. Following this, we employ the same renaming and dropping operations on a Polars data frame as well, ensuring that both libraries yield consistent results. It's akin to making sure that all parts of a machine are functioning in harmony. These steps are vital during the data preparation phase, as clean and well-labeled data lays the groundwork for insightful analysis. Clear labeling helps analysts and stakeholders alike grasp the message of the data more quickly, fostering effective communication and understanding. In striving for clarity, we not only enhance our ability to analyze the information at hand, but also prepare the ground for deeper insights to emerge. As we continue to refine our dataset, we set the stage for more complex analyses that can uncover trends or patterns previously hidden in the clutter. Cell 13. In this code cell, we delve into the intricacies of joining and merging data frames, utilizing two powerful libraries, Pandas and Polars. These libraries are widely cherished in the data science community for their efficiency and ease of use. To kick off our exploration, we begin by constructing a customer data frame, which serves as a foundational element in our analysis. This data frame consists of unique customer IDs that act as identifiers, alongside various segments designed to categorize customers into distinct groups. For instance, you might have segments like frequent shoppers, occasional buyers, and new customers, each representing different behaviors and potential marketing strategies. This foundational understanding paves the way for us to explore how to effectively combine various datasets for richer insights. After establishing our customer data frame, we proceed to employ a left join operation, a fundamental technique in data manipulation, using both the Pandas and Polars frameworks. This left join allows us to merge our customer data with an additional data frame referred to as DF, perhaps containing transaction details or product preferences. The beauty of the left join is that it preserves all our customer records from the first data frame while integrating them with the matching records from the second data frame based on customer IDs. Imagine this process as connecting dots on a map. Each customer ID is a dot, and the join helps us see not only where they are, but also how they are related to other information. Once the merge is complete, we output the first few rows of the combined results derived from both libraries. This output serves as a clear visual representation, illustrating how the data intertwines based on the customer IDs. For example, you may see that the record for a frequent shopper now includes additional columns detailing their purchase history, enabling a richer narrative around that particular customer. This merging process is not merely a technical step. It is crucial for impactful data analysis. By enriching our datasets, we're able to glean deeper insights into customer behavior and segmentation, which can be invaluable for making informed business decisions and tailoring marketing strategies. As we navigate through this process of merging data, we begin to appreciate how effectively combining datasets can unlock new perspectives that might otherwise go unnoticed. This brings us to understand the importance of mastering these techniques, paving the way for more advanced data manipulation and analysis techniques that will follow in our exploration. Cell 14. In this particular code cell, we delve into the intricacies of categorizing financial transactions according to their associated risk scores, a vital task that can significantly impact decision-making processes. To achieve this, we harness the capabilities of two widely used data manipulation libraries, Pandas and Polars, each with its unique approach and syntax. The ultimate goal here is to introduce a new column titled Risk Band. This column will serve as a classification system, assigning each transaction a label of either high, med, or low, depending on the defined score thresholds. To illustrate this concept further, consider a scenario where a financial institution processes thousands of transactions each day. It's crucial for the organization to promptly identify which transactions might pose a higher risk of fraud or default. By implementing a classification system based on risk scores, the institution can prioritize its investigative efforts and allocate resources more efficiently. For instance, if a transaction carries a risk score exceeding a certain threshold, it can be flagged as high, triggering immediate review procedures. Conversely, transactions falling below a specified limit may be classified as low, indicating they pose minimal risk and can be processed swiftly. In our exploration, when using Pandas, we turn to the function np-select. This function allows us to apply multiple conditions effectively, mapping our specific criteria to the desired output categories. By carefully defining the thresholds, we can ensure that each transaction is categorized accurately based on its risk score. For example, let's say any transaction with a risk score above 75 might be classified as high, between 40 and 75 as med, and below 40 as low. This clear delineation helps in systematizing our approach to risk management. On the other hand, Polars presents a different methodology through its intuitive when-then structure. This syntax facilitates similar conditional logic, allowing for the classification of risk scores in a straightforward manner. For instance, in Polars, we can chain together conditions seamlessly, crafting a clear and readable pipeline that leads to the same classification results. Using this approach, we can efficiently manipulate large datasets, ensuring that each transaction is assessed and categorized with both speed and accuracy. Once the coding is executed, we can anticipate an enlightening output that showcases a preview of the modified data frames. This output will display the newly added risk band classification alongside each transaction record, providing immediate insights into the risk landscape. By layout these classifications visually, analysts can quickly assess how many transactions fall into each risk category, facilitating rapid decision-making and strategic responses. In essence, this exercise not only demonstrates the power of conditional logic in processing data, but also emphasizes the importance of effective category labeling in the realm of data analysis. It serves as a crucial building block for developing more complex models and insights, ultimately enhancing the ability to manage risk in financial transactions. With this understanding in place, we can now delve deeper into the nuances of data classification and explore further enhancements. Cell 15. In this code cell, we are embarking on a systematic benchmarking endeavor aimed at analyzing and comparing the performance metrics of two highly regarded data manipulation libraries, Pandas and Polars. These libraries have become staples in the data science toolkit, each offering unique advantages tailored to specific tasks. The primary objective here is to rigorously evaluate aspects such as speed and memory consumption when executing common data frame operations, utilizing a synthetic dataset as our testing ground. To illustrate the task at hand, consider the way a chef assesses two different knives for their efficiency in slicing vegetables. Just as the chef would test each knife by cutting through tomatoes, carrots, and onions, we aim to analyze how each library performs varied operations, both fundamental and sophisticated, on our constructed dataset. The initial phase of this code cell involves importing the necessary libraries, which sets the stage for our analysis. This importation is akin to gathering tools from a workshop before starting a crafting project. You want to ensure you're equipped with everything you might need. Next, we define several utility functions that will not only track memory usage, but also execute the benchmarking tests. This is a crucial step, as monitoring resources provides a comprehensive view of how each library utilizes memory, enabling us to determine which is more efficient when handling large volumes of data. Imagine running a marathon while constantly checking your hydration levels. Staying aware of how much water you have is important for sustaining your energy throughout the race. Following the setup, we generate a realistic synthetic dataset, specifically designed to simulate the types of transactions one might find in the real world. It includes various data points like transaction amounts, timestamps, and categories. Think of this dataset as a test kitchen, filled with ingredients carefully curated to challenge our libraries in meaningful ways. Once the dataset has been established, we define the key operations that will serve as the basis for our comparison. These operations include filtering records based on specific criteria, adding new columns to enrich the dataset, grouping data to summarize key insights, sorting records for better organization, and even reading from CSV files to simulate real-world data import scenarios. Each operation is effectively a task that tests the library's capabilities, allowing us to observe their strengths and weaknesses. For each operation, we implement corresponding functions for both Pandas and Polars. This parallel execution serves as a direct comparison, enabling us to analyze how each library approaches the same tasks and the efficiency with which they deliver results. It's much like comparing two athletes competing in the same race. While they might have different techniques and styles, the ultimate goal is the same. The insights gained from this benchmarking exercise are invaluable for developers and data scientists alike. By understanding the performance intricacies of each library, one can make informed decisions about which tool to leverage for particular projects. For instance, if a developer needs to process a large dataset in real time, they might find Polars to be the faster choice, while for intricate data wrangling with smaller sets of data, Pandas might still hold its ground with user-friendly features. In conclusion, this benchmarking setup not only serves as a technical evaluation, but also positions developers to choose the right library based on specific performance criteria that are crucial for efficiently processing extensive datasets. With our testing framework and synthetic dataset in place, we are ready to dive into the performance results, further illuminating the strengths and weaknesses of pandas and polars in this comparative analysis. Cell 16. In this cell, we delve into a comparative analysis of the performance metrics associated with the polars and pandas libraries, specifically when executing various data operations that are integral to data analysis and manipulation. This examination brings to light a remarkable finding. Polars demonstrates a significantly faster execution speed than pandas across a range of tasks, including, but not limited to reading CSV files, filtering datasets, adding columns, grouping data, and sorting. The performance improvements observed are striking, with speeds observed to be anywhere from 9 to an astonishing 43 times faster than those recorded for pandas. This distinction carries considerable weight for individuals or teams working with expansive datasets, as it suggests that adopting polars can lead to a substantial reduction in computation time, ultimately resulting in improved efficiency and allowing data analysts to focus more on deriving insights rather than waiting for data to process. For instance, consider a data analyst trying to filter millions of rows from a dataset. Using polars, this task could be completed in mere seconds, freeing up precious hours in comparison to the slower pandas method, which might take significantly longer. However, it's important to take into account the differences in memory allocation that arise between the two libraries. While there are instances where polars may allocate more memory during its operations, this shouldn't be misconstrued as an indication of greater overall memory usage. It's akin to the difference between a powerful sports car that might consume more fuel when going at high speeds, but still offers better fuel efficiency over longer distances compared to a standard sedan. Understanding these nuances enables users to make educated decisions when selecting the most suitable library for their data processing needs, tailored to the unique requirements of their specific projects. With this insight, you can better navigate the landscape of data manipulation, setting the stage for a deeper exploration of their respective functionalities and use cases. Cell 17. In this particular cell, we observe a seemingly straightforward comment that succinctly states, "We have reached the end of the notebook." Although it consists of just one word, that word carries significant weight because it marks the conclusion of our journey through this Jupyter notebook. This simple but profound statement serves multiple purposes. It not only signifies that we have completed our exploration of the material, but also invites users to take a moment to pause and reflect on the insights they've gained throughout the process. Think of this ending as the closing passage of a well-written book, just as an author wraps up the narrative, tying together themes and ideas that have surfaced over the chapters. This phrasing reinforces the completion of our analysis and discussions. This moment of closure is vital because it offers a chance for users to revisit the key concepts we've covered. Much like how one may return to a favorite passage or an important lesson in a beloved text. Moreover, signaling the conclusion allows anyone perusing the notebook to understand clearly that the detailed exploration is finished. This clarity is especially useful in collaborative scenarios where multiple individuals may engage with the same notebook. It prevents confusion and ensures that everyone is on the same page, quite literally, as they move forward. Just as a signal flags the end of a race, prompting runners to catch their breath and reflect on their performance, this comment provides a cue to the users that they can now step back and consider the broader implications of the analyses we've just navigated. In essence, this final comment encapsulates the entire experience, encouraging users to not only appreciate the work done, but also to think critically about what they've learned and how they may apply that knowledge in future endeavors. With this thoughtful transition into reflection, we can now carry forward the insights gained here and look toward new avenues of exploration that await us.